Welcome back. In this video, I'm going to solve exercises 9 to 13 of chapter 1 about the Stone-Weierstrass theorem. First exercise, the exercise number 9. We have a compact metric space X, and we suppose that a finite collection of continuous functions separates the points of X. We have to show that actually X is homomorphic to a subset of Rn. Okay, so this is a really extreme case, okay, because usually we need an infinite collection that separates the points of X. So consider the function capital Phi from X to Rn, whose components are the Fi. Okay. So we have n components. Okay, we will show that actually phi is continuous, is a homomorphism actually from X to its image. Okay, so first of all, it's continuous because each component by assumption is continuous, because each fk is continuous. Next, phi is injective because if X is different from Y, then by assumption, since the collection f1, fn separates the points of X, then there exists one of them, fk, let us say, such that fk of X is different from fk of Y. So at least one component of phi of X will be different from one component of phi of Y. So phi of X cannot be equal to phi of Y. So this proves injectivity. Therefore, phi is a continuous bijection from X to its image. Okay. Now, how do we prove the continuity of the inverse? This is actually a theorem on topology, which states that if the domain is compact and the range is Hausdorff, then automatically phi minus 1 is continuous, because continuity of phi, since it's a bijection, is equivalent to the fact that phi is a closed map. So it maps closed sets into closed sets. Okay. So if you don't know this, it's very easy to prove. Proving that phi minus 1 is continuous is equivalent to proving that the inverse image of under phi minus 1 of a closed set is a closed set. But the inverse image under phi minus 1 is just the direct image under phi. So if capital A is closed in X, then it's compact. And since phi is continuous, phi of A is compact as well. So we have a compact subspace of Rn, and therefore it's closed. So phi maps closed sets into closed sets, and this is equivalent to the continuity of phi minus 1. Okay, so we proved that, in other words, X can be embedded in Rn. Okay, next exercise. A direct application of the classical Stone-Weierstrass theorem, which states that every continuous function on a compact set, on a compact interval here, can be approximated by polynomials. Okay, so first, we are given a continuous function f from the compact interval ab into R, and we have to prove that there exists a sequence of polynomials such that the integral of fpn converges to the integral of f squared. Okay, so we know that there exists, since f is continuous and ab is compact, there exists a sequence of polynomials which converges to f uniformly, or in the supremum norm or the maximum norm. Okay, so just now consider the difference between the integral of fpn and the integral of f squared. So when we put everything inside one integral, we factor by f of x, because the integral is linear. And now the integral of some function is the absolute value of the integral is less than the integral of the absolute values. Now Pn of x minus f of x is less than the norm of Pn minus f, because the norm infinity is just the maximum. So when we put it outside, we are left with the integral of the absolute value of f, which is just the norm 1 of f. And so this is just a constant, and this quantity tends to 0 as n tends to infinity. So this difference tends to 0, and therefore the integral of fPn converges to the integral of the square of f. Okay. Now, second question, we have that the integral of f against any power of x is 0. So by linearity, this implies that the integral of f against any polynomial is 0 again, because a polynomial is a linear combination of monomials. Okay, so p is just the sum of ak p xk. So the integral of f against any polynomial is 0. So in particular, if we take the polynomial in the previous question, a sequence of polynomials Pn, then the integral of f against Pn is 0, and this converges to 0. But according to the previous question, it converges to the integral of f squared. Therefore, the integral of f squared is 0, and continuity of f implies that f is actually 0. Okay. So this concludes exercise number 10, a classical exercise on Weierstrass approximation theorem. Next exercise, we asked this question in the exam of last year, second session. So we consider a general compact metric space, and we consider the collection of all Lipschitz continuous functions, real value, of course. So I have to show that this collection, calligraphic A, is a subalgebra. It separates the points of x, and we have to deduce that it's dense. So otherwise stated, we can approximate any continuous function on x by Lipschitz continuous functions. Okay, here, the nature of x is very general. It's not necessarily an interval or a subset. It can be anything. Okay, so of course, Lipschitz continuous functions are better than just continuous functions. Okay, why is it a subalgebra? So we have to prove that calligraphic A is stable under addition, multiplication, and multiplication by scale. So consider two elements fg in A, two Lipschitz continuous function, and a constant alpha in R, and two arbitrary points xy in X. We have to show that f plus g is in A, fg is in A, and alpha f is in A. Okay, so first the sum. We just write the condition for f and the same condition for g, and use the triangle inequality. By the triangle inequality, we get kf dxy plus kg dxy, so we can factor by the xy. So the sum of two, and this is something that we expect, the sum of two Lipschitz continuous maps is Lipschitz continuous again. Okay, and for the multiple of f, just multiply by absolute alpha, because alpha could be negative. So a multiple of a Lipschitz map is a Lipschitz map again. Okay, but the constant changes. Okay, for the product, so now we know that calligraphic A is stable under addition and multiple, so it's a subspace. Okay. Now the multiplication is a little bit less trivial, but we use a trick that you should know, a fundamental trick in analysis. So we use the triangle inequality. So we consider f times g minus, so fx gx minus fy gy, and we add and subtract fx gy. So the triangle inequality tells me that this difference is less than these two. Now, if we look at the first absolute value of the first term, we can factor by f of x. And in the second term, we can factor by g of y. Now, f of x in absolute value is less than the supremum norm of f, because this is just the maximum. And same thing for g. So g of y is less than norm infinity of g. Okay. And now we apply the assumptions. G of x minus g of y is less than a constant, kg, times the distance. And same thing for f of x minus f of y. So we get dxy in common, and then we factor, and we get a constant, which is the norm of infinity of f times the constant, the Lipschitz constants for g, plus the same thing, vice versa. And this is a constant. So this means that fg is Lipschitz continuous again. So therefore fg belongs to A, and so A is stable under multiplication, and therefore it's a subalgebra. Okay, next, you guess, we need to prove two things. We need to prove that A separates the points of x, and A contains the constant function, which is trivial, of course, because a constant function is Lipschitz continuous. Okay, separation is a little bit less trivial because we don't know well, but if we recall that distances are Lipschitz, so we fix x because x is given, and we consider the function defined by f of z equal the distance between x and z for z and x. Okay, so this is a function. Now the first x is fixed here, so it's a function of z. And now, by the triangle inequality, if we evaluate f of z1 minus f of z2, we get dx_z1 minus dx_z2, and by the second form of the triangle inequality, this is less than the distance between z1 and z2. So this proves that this function is Lipschitz continuous. So it belongs to A with constant 1, actually. And now this f separates x and y because f of x is the distance between x and x by definition, so it's 0. And f of y is the distance between x and y, and this is different from 0. It's positive because x is different from y and d is a distance. So we separated x and y by a Lipschitz continuous function. And okay, so as we know, constant functions are Lipschitz continuous. So we have now the three assumptions. We have a subalgebra which contains the constant functions and separates the points of x. Therefore, by the Stone-Weierstrass theorem, it is dense in the space of continuous functions from x to r, equipped, of course, with the supremum distance that we defined in the lectures. Okay, so convergence in the space is just uniform conversion. Okay, so this is a typical exercise. Now we move to so the last two exercises actually are about the complex form of the Stone-Weierstrass theorem, because we said in the lectures that it's important to work to consider functions from a compact metric space into R. But what happens if we consider continuous functions from x to c, the complex plane? Okay, so the real form does not hold when we replace R bar C. So we need an extra assumption. Okay, so the purpose of this exercise is to give a counterexample. So here we consider the unit circle that we denote by S1, as you know. So it's a subset of the complex plane. It's the set of all complex numbers whose modulus is 1. And we consider the set of all polynomials in the variable z, but we restrict them to the unit circle. So first question, we have to show that this collection, calligraphic A, is a subalgebra of the algebra of continuous functions from the unit circle to C. Okay, so complex continuous functions from the unit circle to C. And it contains the constant functions and separates the points of S1. However, it's not dense. Okay, so this is we announced this in the lectures that when you replace R by C, the theorem does not hold. So we need an extra assumption, and this will be done in the next exercise. Okay, so the first question is easy because the sum and product of two polynomials in Z is again a polynomial in Z, and the multiple of a polynomial in Z is a polynomial in Z, so it's straightforward. Okay, constant functions, of course, the constant polynomial equal 1. The constant function equal to 1 is a polynomial, of course. Just take A0 equal 1. And separation, just take the identity. So if you have two distinct points, Z1 and Z2, take the identity polynomial, just P of Z equals Z. Then we have P of Z1 is different from P of Z2. So it's just straightforward. Okay, so we have the condition of the real version of the Stone-Weierstrass theorem. Now, we'll show that A, however, is not dense. So we consider the symmetric function, symmetric with respect to the x-axis. To each z associates its conjugate. Of course, it's continuous. So we are asked to compute the integral over the unit circle, positively oriented, of this function. And then we'll have to compute the integral over any polynomial. And then we have to deduce a contradiction. So we have to deduce that f cannot be approximated uniformly by polynomials. Okay, so unlike the identity is a polynomial, but z bar is not a polynomial. Okay, and it's not only not a polynomial, it cannot be approximated by polynomials uniformly. So this is a straightforward question that we know from the complex variable course. Just have a parameterization of gamma of S1, which is just EIT cosine t plus I sine t. So just go back to the definition and replace z by gamma of t, and you have to multiply by the derivative of gamma, which is I EIT. So when you do that, we simplify. We have E minus IT because the conjugate of EIT is E minus IT, as you know. So we get the simplification and you get 2 pi I. Okay, this is something that you did several times. However, now if P is a polynomial, as we know, all monomials actually possess antiderivatives. Actually, all powers of Z, even negative powers, possess antiderivatives except Z minus 1. Okay. So, and we know that if a function possesses an antiderivative, then by Barrow's rule, the integral over any loop is 0. Okay. If you don't believe me, just compute that. So just compute zk, and then you do the summation. Okay. Now, last question. Suppose by contradiction that this function z bar can be approximated uniformly on the unit circle by polynomials by elements of A, and take epsilon between 0 and 1. So then by our assumption, there exists a polynomial whose distance to f in the infinity norm is less than epsilon. So by the fundamental estimates of integrals, first we write the difference between the integral of f and the integral of p, and we write them inside one integral. And now the absolute value, the modulus of the integral, is less than the length of S1 times the maximum of fz minus pz, okay, which is less than epsilon. So the difference is less or equal than 2 pi epsilon. However, this is 2 pi I and this is 0, and so we get modulus of 2 pi I is less or equal than 2 pi epsilon. So we get 2 pi less or equal than 2 pi epsilon. So simplifying by 2 pi, we get epsilon bigger or equal than 1. But this contradicts our choice of epsilon. So our approximation property does not hold in this case. So, so A is not dense in the space of continuous functions from the unit circle to C. Okay, so therefore, if we want to save the Stone-Weierstrass theorem in its complex form, we need to put an extra assumption, and this is what we shall do now. This is the assumption. So we have to assume that in addition to the 3 requirements, that it's a subalgebra, contains the constant function, separates the points of x, we need the extra condition that A is stable under conjugation. So if f is an element of the algebra, of the subalgebra, then its conjugate should also be an element of the subalgebra. And this condition, this 4th condition, was not satisfied in the previous exercise because the conjugate of a polynomial in Z is not a polynomial in Z, it's a polynomial in Z bar. Okay. So now so the purpose of the exercise is to deduce this complex form of Stone-Weierstrass from the real form, okay, but under the additional extra assumption that it's stable under conjugation. So for this, we consider the collection of all elements of the form the real value of f when f is in A, and A2 the imaginary part of f where f is in A. So we have 2 subsets now of A. So we have to prove that A1 equal to A2, and they are both subsets of A. Then we have to prove that A1 is a subset of continuous functions from x to R, because the real part and the imaginary part are real values. So A1 equal to A2, and it's a subset of CXR, and we have to prove that they are dense in CXR, and then we have to conclude that the original A is dense in CXC. Okay, so we deduce the complex form from the real form, but with the extra assumption, of course. So because we know that if we don't put this assumption, the result is wrong. Okay, so take an element f in the subalgebra. Okay, we know that the real part of f is 1/2 of f plus the conjugate of f. We know that. Now, since a is an algebra, it's stable under addition and multiplication by scalars. So if f is in a, the assumption, the condition, the fourth condition, if f is in a, then f bar is in a. So f plus f bar is in a because a is stable under addition. And then when we multiply by 1/2, we get an element of a. So this proves that any element in A1 is actually an element in calligraphic A, first thing. Now, why similar for A2? So now, but why they are equal actually? Because as you may check, the imaginary part of a complex number, well, in this case, a function f, is the real part of minus if. This is just simple algebra, because if f is u plus iv, or f1 plus if2, then minus if is minus if1 plus f2. So we get the f2, the same f2. Okay, so the real part of this is the imaginary part of, and similarly, the real part of f is the imaginary part of I times the conjugate of f. Just simple algebra. So any element in A1 is an element in A2 and vice versa, because the real part of an element in A is the imaginary part of another element in A, because if f is in A, then minus if is in A, and if f is in A, then if bar is in A. So the condition. So A1 is actually equal to A2. Now, why A1 is then? So we have to just check the three properties, the three conditions of. So we have, first of all, A1 is a subalgebra. Why? So to prove that, we need three things: a stability under addition, multiplication by scalars, and multiplication. So now if we take two elements in A1, so we can write them as real part of f and real part of g. Their sum. So real part of f plus real part of g is just the real part of the sum. When we multiply by a real number, so the real part of alpha f is alpha real part of f. Okay, so, and third thing, the product of two real parts, so real part of f times real part of g, we can write real part of f as 1/2 f plus f bar, but according to second property, we can put it inside the real part. So the product of real f real g is the real part of this of 1/2 f plus f bar g. And now if f and g are in A, then f bar is in A. So 1/2 of the sum is in A and g is in A. So the product is in A. Okay, so we know that now A1 is a real subalgebra of Cx. Okay, and of course A1 contains the real constant functions. And it separates the points of x because why? So since calligraphic A contains the constant functions, we just take the constant function to be just 1. So and 1 is the real part of 1. And why does A1 separate the points of x? Because if you take 2 points x and y in the space x, then since calligraphic A separates the points of x, then there exists f in calligraphic A, which is complex valued, such that f of x is different from f of y. If two complex numbers are different, then either the real part are different or their imaginary parts are. But in both cases, if this is true, then just this is the real part of f is an element of A1. So we get an element in A1 whose value at x and y are different. And same thing, the imaginary part is an element of A2, which is just A1. Okay, so we conclude that A1 is dense in the space of continuous functions from x to r. And now we just have to conclude that what does density means? It means that any element in A1 in CXR can be approximated by an element in A1. So in particular, if you have an element in calligraphy K, which is a complex valued function, its real part is in CXR. And the real part of F can be approximated by a function. So what does this mean? It means that for every epsilon positive, there exists an element G in A1 such that the distance between real F and G is less than epsilon. And similarly, the imaginary part of F minus an element H in A1 is less than epsilon in the distance, the maximum distance. So if we use the triangle inequality, then F minus G plus IH, if they use the triangle inequality, is less than 2 epsilon. So just have to write this. It's very easy. Okay, so this proves the complex form of the Stone-Weierstrass theorem and concludes exercise 13. So the exercises we are done now with the exercise of chapter 1. And in the next video, I'm going to start chapter 2. So thank you for your attention and see you next time.